Today, we are going to do a super focused revision of one of the most important units, algebra. We're going to blitz through the entire thing, making sure you feel absolutely solid and ready to crush those exams. Let's get started.
So here's our game plan for this algebra deep dive. We'll kick things off with sequences and sigma notation, then jump into exponents and logs, tackle the binomial expansion, get into the more advanced stuff like induction and complex numbers, and finish strong with systems and partial fractions. Basically, we're covering all the bases for Unit 1.
First up, sequences and series, which is really just the math of patterns. We're going to focus on the two big ones you'll see on your exams, arithmetic and geometric sequences. And of course, we'll cover that powerful sigma notation for summing them all up.
Okay, so what's the difference between these two? It's actually really simple. An arithmetic sequence just adds or subtracts the same number every single time. That's your common difference, d. A geometric sequence, on the other hand, multiplies or divides by the same number, your common ratio, r. You can think of it as linear growth versus exponential growth. Now, these are your go-to tools for any arithmetic sequence, and good news, they're right there in your data booklet. The first one lets you find any term you want, and the second one adds up the first n terms for you. But remember, knowing what they do is way more important than just knowing where to find them.
This is a classic IB-style problem. They'll give you a couple of terms from way down the line and expect you to work backwards to find the first term and the common difference. The trick is always the same. Just set up two simultaneous equations using that nth term formula and solve for your two unknowns, d and u1.
Okay, let's talk about sigma notation. I know it can look a little scary at first, but it's really just a fancy, compact way to say add up a bunch of stuff. The number on the bottom tells you where to start counting, the number on top tells you where to stop, and the formula right next to it is what you plug those numbers into. It's a super efficient tool for series.
Moving on to exponents and logarithms. You gotta think of these two as two sides of the same coin. They're inverses of each other. Exponents are all about building things up with multiplication, and logarithms are all about breaking them back down. If you get that relationship, you've pretty much mastered both. These laws of exponents, you need to know them like the back of your hand. Seriously, they are the fundamental grammar of algebra. Once you have these down, you'll be able to simplify really messy expressions with no problem at all. And look at this, the laws of logarithms are a perfect mirror image of the exponent laws. See how adding logs corresponds to multiplying the numbers inside, and subtracting logs means you're dividing? That's not a coincidence. It's because of that inverse relationship we were just talking about.
This is where logarithms are an absolute game changer. Whenever you have your variable x stuck up in an exponent, logs are how you get it down. You just take the log of both sides, use that power law, law 3, to bring the x down in front, and then boom, it's just a simple algebra problem.
All right, let's switch gears to the binomial expansion. This is an awesome shortcut that lets you expand something like a plus b to a really high power without wanting to pull your hair out multiplying bracket after bracket after bracket.
One of the coolest ways to find your coefficients is with Pascal's triangle. It's this really elegant pattern where you just add the two numbers above to get the one below. If you need to expand to the power of n, you just go to the row labeled n, and there are all your coefficients ready to go.
Now, for bigger powers, or if you only need one specific term, the official binomial formula is your best friend. And check out the pattern here. The power of a always starts high and goes down, while the power of b starts at 0 and goes up. That NCR part is the coefficient, which thankfully we can find super easily with our calculator.
And this right here is probably your biggest time saver on the exam. Do not try to calculate NCR by hand. Your GDC has a function for it almost always under the probability menu. You just type in n and r, hit enter, and you get the coefficient in seconds. It's a lifesaver.
Okay, time to level up. We're now diving into two of the more abstract but really powerful topics in this unit, proof by induction and the amazing world of complex numbers.
Proof by induction. A good way to think about it is like climbing an infinite ladder. First, the base case. You prove you can get on the first rung, which is usually n equals 1. Next, the inductive hypothesis. You just assume you're standing on some random rung k. Finally, the inductive step. You prove that if you're on rung k, you can definitely get to the next one, k plus 1. If you can show all that, you've basically proven it's true forever.
So, complex numbers came about because mathematicians needed a way to deal with things like the square root of -1. So they just invented a number for it and called it I.
Every complex number has a real part, A, and an imaginary part, B. And this literally opens up a whole new dimension of math for us to play in.
And this is how we see them. We plot complex numbers on something called an Argonne diagram. It's just like a regular XY graph, but with a twist. The horizontal axis is for the real part, and the vertical axis is for the imaginary part. Every single complex number has its own unique spot on this plane.
Now, here's the golden rule for dividing complex numbers. You cannot have an I in the denominator. So how do you get rid of it? You use this awesome trick. Multiply the top and bottom by the conjugate of the denominator. The conjugate is just the same number, but with the sign in the middle flipped. This always, magically, makes the denominator a real number, and then you can simplify.
All right, let's bring it home with our final section. We're looking at two really essential skills: figuring out what the solutions to systems of equations actually mean, and the technique of partial fractions, which is all about deconstructing big fractions into smaller, simpler ones. When you solve a system of linear equations, what you're really doing is finding out where the lines or planes meet. And when you think about it geometrically, there are only three things that can happen. They cross at one single point, giving you a unique solution. They're parallel and never ever cross, which means no solution. Or they're actually the exact same line, giving you infinite solutions.
Partial fractions is a huge skill, especially for when you get to calculus and integration. All it is, really, is the reverse of adding fractions together. You start by factoring the bottom, you set up this template with A and B as your unknown tops, and then you use some clever algebra to figure out what A and B have to be.
You know, this quote just nails what this algebra unit is all about. Every single topic we've covered today, sequences, logs, binomials, they're all just incredibly powerful tools designed to take a problem that looks really complicated and make it simple and elegant to solve.
So, we've gone over all the tools and the techniques, but the real magic of algebra is when you apply it to the real world. You could use a geometric sequence to model compound interest on your savings, or use complex numbers to analyze electrical circuits. The how is what gets you the points on the exam, for sure, but the why? That's what makes math so cool. Keep practicing and good luck.